Dear Professor Hoften, thanks a lot for giving us the opportunity to present today to your network in Pomerania about our AI-based approach for neuroradiology. We are quite young but innovative startup company from Germany, located in Berlin, but also with offices in Heidelberg. And in Heidelberg, actually, they were the roots of the company. As two medical physicists, namely Dr. Lemke and Dr. Döpfert, founded the company together with two radiologists from Germany and the business angel. And in particular, from the radiological side, from the beginning, there was a clear mandate to say, okay, what they really needed was a robust brain volumetry solution that was supposed to be installed locally to avoid all hassle with data privacy rules, but also to have the results available very fast. And the same should happen at a fair price in order to make it accessible to a broad basis of radiologists and to avoid an area tower phenomenon that only university centers are able to use those technologies. Yeah. We presented the first prototype in 2018, so quite after the foundation of the company, and licensed our first medical product, MD Brain, at that time more focused on volumetry, early 2019. From there onwards, we worked in innovation cycles of every 4 to 5 months, releasing new medical products with extended features and also higher precision. At the moment, we provide an MD Brain software solution for volumetry and lesion characterization, version 3.4, and also provide its licensed medical product in lesion detection tool for spinal cord lesions. How the system works is that we take MRI images, apply methods of machine learning, deep neural networks, but also classical machine learning to provide segmentation, both in terms of regions of interest, different brain regions, to perform volumetric analysis, but also lesion analysis. In terms of the volumetry, we are able, or in large normal cohort of almost 6,000 normal people allows us for each patient at each age and a normalization. So we can derive individual normal values for each patient based on age, but not only age, but also sex and intracranial volume. Yeah. And by doing that, we apply two thresholds. The classical definition of normal values being 2 standard deviations left and right. Everything that is beyond or outside this normal value is colored yellow in the resulting reports. Everything that is outside 4 standard deviations outside is colored in red. And you see from distance already that the structured reports allow you an easy capture and fast capture of the pathological findings, both in terms of color-coded tables, but also schematics. And for the lesion segmentation, of course, we don't compare to normal values, but to prior exams to make the assessment of lesion dynamics easier. Yeah? And if you look at the picture for a second, I think you can get that we provide two advantages to the classical way of working in radiology. Number one, we evolve here in terms of volumetry from just experience-based judgment on, for instance, whether the brain volume is still normal or whether there's an atrophy, yes or no, where you have a high inter-rater variability. So we can make it very clear by a quantitative analysis and a comparison with normal values to overcome the subjective assessment. In terms of lesion segmentation, we save a lot of time, in particular if you think on a patient with a medium lesion load. It can be quite time consuming to compare whether there is a progress of multiple sclerosis, for instance, or not. And these are the main areas that we provide solutions to. Look at the resulting reports. You have a 2-page volumetry report. Page 1 is more the visual, most relevant findings. The page 2 is more granular in a tabulated form. And for the lesion report, you see here representative slices of the patient, and also in tabular view of the data. If you look at the volumetry report in a second, you see that we built a bridge here from the classical view of looking at the MRI images, the subjective view, by pre-cutting it according to standard locations. We provide on page 1 the quantitative assessment of the global volumes, meaning whole brain, total white matter, total gray matter, and cerebral cortex. You see the schematics of the report, all the lobes, including the hippocampus, all the ventricles, and for selected regions, meaning whole brain, gray matter, mesiotemporal, hippocampus, frontal lobe, parietal lobe, and the lateral ventricles. Together, we provide also the opportunity to plot prior scans or data points from prior scans over the age of the patient. And all the tables are set up in a similar way. Here, an example from the second page for supratentorial volumes. You have the normal range. You have the for the most recent 2 time points, the absolute volume that was determined by the system, and then the derived percentile value. You see, percentile below approximately 2.5 is pathological, and as 55.2 is below the lower threshold of the normal range. This is a pathological value. But more, looking at or interpreting the data, you would only look at the percentiles, of course. The additional feature, as I mentioned, is those longitudinal percentile plots. Here's an example from a patient where you see a sharp decline of the mesiotemporal volume in the patient. And if you do that with the same scanner, with the same parameters, you can derive at least an idea that there's something is going on in neurodegenerative process, in spite of the fact that in absolute terms, the most recent value did not reach the pathological range yet. And in particular, if you, let's say, normalize it or use the lateral ventricles as a control, this is quite striking. So we can even derive from that dynamics some conclusions. You might ask, how precise is the methodology we use? And we did some internal, of course, external benchmarking. Just pull one piece of data here. We used free surfer. So some of you might know that, developed by Harvard Medical School, is freely available and widely used in academia to look at reproducibility first. For that, we have chosen a public database, the Myriad studies, an Alzheimer's study from the UK. And the nice thing with that study is that you have 178 repeated measurements of the study. That means person has been measured once and then twice again, and ideally you would expect to have the same result. And we did it with FreeSurfer and with MD Brain. And you see here 2 things. Number one, that the reproducibility in terms of percent deviations from the mean of at least 2 measurements is significantly lower with MD Brain than with FreeSurfer. And you also get an idea about the absolute variance, which ranges between 0.2, 0.3 for the whole brain and approximately 0.7 for the third ventricle. And if you keep in mind that the physiological variance over a year in a healthy subject is approximately 0.1 to 0.3%, you're in that range for the whole brain. We also looked at precision in terms of robustness, of whether MD Brain can differentiate an Alzheimer group from a healthy control group of volunteers from the same study, Myriad study, and what you expect would be hippocampus and temporal lobe would be most discriminating between the 2, and that's what you exactly see here in the AUC ROC analysis. And if you take both regions together, you get the sensitivity of 0 and the specificity of 0.91. Of course, this is cohort dependent, but that's what we published at ECR last year. If you look at the brain lesion report, the system would automatically select the, if you provide it with prior scans, it would automatically select the representative slices with the largest dynamics in terms of new enlarged versus old lesions, would color code the same, and in the corresponding slices also give you feedback, also color-coded on the regional distribution of those lesions. And this is derived from the Magnums and McDonald's criteria in order to differentiate rather MS-specific from unspecific regions. So we analyze the typical MS-specific periventricular juxtacortical infratentorial lesions, differentiated from the unspecific subcortical or deep white matter lesions. As a result, you get also a quantitative output of the same in terms of lesion volume, total and per region, and then split out into new and enlarging lesions, all based on FLAIR images. And also here we try to gain as much as possible data, comparing it to academic standard solutions presented here at EAN last year, using 3 Tesla MRIs from the LIT-MS study, which provided data from 28 patients, original images, ground truths based on consensus reading of trained neuroradiologists, LST and SLS as academic solutions versus MD Brain. And you see here, before looking at the overall numbers, here in this example with the patient for high lesion load and low lesion load, that in contrast to the academic standard solutions, MD Brain performed better on smaller lesions in particular, leading to a higher F1 score as compared to the academic standard solutions, and a little bit better DIE score, measuring the congruence of the annotations. On top of that, just as a side remark, we also provide an MD spine report, which we provide since end of 2020 for interested centers. One of the limitations at the moment only that it's only valid for 3 Tesla MRIs. Try to extend it to 1.5 Tesla, but at the moment it only works with 3 Tesla MRIs. Providing the same axial and sagittal view and quantitative analysis of the lesion based on T2 images. Said in the beginning, one of the mandates was to provide an on-premise solution, something that runs locally inside the local IT architecture in a central, to provide fast and reliable and secure data analysis, and that's what we do. Inside the IT system of a customer, we provide those standardized reports that I've shown you already. We receive the data from the PACS, in some instances already from the scanner directly. It undergoes a quality control here in the MD Brain server. If it's okay, the automatic analysis is triggered. On top of it, as this is a local computer or server inside the local IT of a center, it can be used to communicate with the system. Right? This is all closed loop. You can't interact. You may be able to supervise it in the PACS, but you can't interact with the system. We provide a platform, a web-based platform or browser-based platform. You can access the system with an ordinary web browser, and you will be able to follow the patient list and patient digital records, the digital reports. And on top of that, you're able to supervise the system on a single lesion basis via a built-in 3D viewer. And here you're also able to change the annotations. So that means if you're interested in a hybrid model of an artificial intelligence system as MD Brain with human intelligence to make it perfect according to your local standards, then you can do that with an easy-to-use tool built in to the platform. Just as a side note, the system also has certain built-in export functions that you can export all the data for further statistical analysis. Yeah. Technical requirements are quite mild, I would say. The system needs a virtual server or a physical one with 4 cores, Intel i7 or compatible 16 gigabit RAM, 500 gig HDD. You can accelerate the processing time significantly by using a graphic board. And then you end up with times between image acquisition and providing a report of approximately 5 minutes only. You need, of course, a local network that is fast enough in order not to be the bottleneck. And for installation and maintenance, we would request a remote access. We work platform independent with field strengths 1.5 to 3 Tesla, with Siemens, Philips, GE, Toshiba scanners. In terms of input data required for neurodegenerative questions, we needed native 3D T1, ideally MQH. For lesion detection of the brain, 2D or 3D T1 plus 2D or 3D T2 flares. And for the spinal cord, axial and or sagittal T2s. We are, as I mentioned in the beginning, certified medical product, and as a company, our quality management is also certified as a certified producer of medical devices according to European law. Just a snapshot, a selection of the, in particular, scientific collaborations we have at the moment ongoing, and besides our current products, MD brain, MD spine, we're working on extensions of the same in terms of aneurysm detection at the moment, brain tumors, but also outside CNS indications in terms of orthopedic indications like knee MRIs and potentially later prostate MRIs. And if you would like to learn more about the system, feel free to reach out to me. And if you would like to join us in providing a second pair of eyes to the radiology community, built on artificial intelligence, I would be delighted to hear from you. Thanks a lot.